Well, hello everyone. It's good to see you guys back here today. Now, almost 4 years ago, I asked the question, could you use air as a refrigerant? Well, clearly the answer is yes. And at that time, I showed an air cycle machine. I built this little demonstrator for it, and we saw how it could cool the air. Thing is though, that demonstrator was really bad. The turbocharger was completely burned out, and I didn't even have a proper oiling system for it. I knew I could do better, and I really wanted to show it to you guys. So I've been hard at work rebuilding the air cycle machine demonstrator, and I'm ready to show it to you today. So as you can see, guys, I have rebuilt the air cycle machine demonstrator, and I'm going to give a quick rundown for anybody who doesn't understand the very basics of the plumbing and how this works. So just as before, this is the air compressor. Air enters here through the air inlet. It's discharged through this pipe, and we have a pressure gauge so we can read the pressure. The discharged air goes into the turbocharger's compressor here, and out of the turbocharger's compressor it comes down this pipe. Yeah, that is a weird angle, but it is what it is. The hot compressed air goes down this pipe and goes into the intercooler. And as you can see, 4 fans now helps tremendously with cooling. And out of the intercooler, it goes into the turbine, which causes the air to expand and get cold. You can see the turbine housing there, and below that you'll see an oil pump, and there's a pressure gauge on the oil pump. Yeah, I know these things are actually meant to like lubricate lathes and mills and stuff. It does work in this application. In the previous video I mentioned that this turbocharger leaks a little bit of oil, but I don't think it really matters too much. It's not in a car, so it's not like we're going to burn oil. Let me show you the power supply. So this box that I've opened, in there is the power supply that sends power to the variable frequency drive. Remember, this is a 3-phase compressor. I need the variable frequency drive and the power supply so I can go from single phase 240 volts AC to 3-phase 240 volts AC or more. The point is, this variable frequency drive can control the speed of the compressor, meaning that the compressor speed in some of the runs is higher, and in some of the runs it's lower. So we can see the effect that it has on the thermodynamics of this cycle. That's the basic explanation. I will tell you the model name and number of these parts later in the video. So you look inside the turbine housing, you can see the turbine in here. You'll get to see that spinning quite furiously later in this video. And the feed line for the oil. So we get oil into the bearing into the turbocharger. And this is the compressor bypass valve. So I did end up putting a little bit of sealant on that gasket material. I don't know if that was necessary. So far though, so good. No leaks coming out of here. Seals up nicely. Up next, I'm going to show you some clips of the air cycle machine running. Now, some of you may notice that there's some foaming in the oil. That's because the turbocharger seals are leaking. So far, it doesn't seem like this is a problem. But even if the turbocharger should fail, it still did produce some good clips that you're going to see right now. And now, a brief message from my sponsors. Treat. Come here. Can you speak? Speak. There you go. Okay. Come here. Spin. Good doggies. So in the third run, we briefly saw the thermometer flash 46.5, measuring air coming out of the turbine, and the discharge pressure was just shy of 4 psi. We saw the intercooler exit air temperature briefly flash 85.4 degrees. Now for a brief moment, it looked like something came out of the turbine besides just air. That's not oil, and we're going to see what that is in the next two clips. Now in run number 4, we briefly saw the thermometer flash 46.1 degrees coming out of the turbine. We also see that the compressor is running at a pressure of 4.5 psi, and that's because I increased the speed of the compressor with a variable frequency drive compared to run number 3. And if you look closely, the intercooler's air temperature also flashes for a brief moment 87.4, so this is further evidence of the increased output power. But what's most apparent is the fog that's coming out of the turbine. Now this is water vapor out of the air that's condensing. This is happening because due to the increased output power, the cooling power is now sufficient to condense water vapor out of the air. This is going to take a lot of energy and cooling power to do because the latent heat of vaporization of water vapor is quite high. But let's check out the final run. So in run number 7, the thermometer briefly flashes 45.9, and this is the lowest temperature that we've seen yet. Also, we can see that the pressure gauge is now reading just shy of 5 psi, the highest pressure that we've seen yet. We also see that the intercooler's temperature flashes the highest value we've seen yet. It briefly shows 88.8. So the evidence is obvious. This is the fastest that I've run the compressor for this filming run. But what might seem unusual to some viewers is that even though there's definitely increased output power, the temperature hasn't fallen by that much, but yet the fog coming out of the turbine has become much more dense. This is because the air cycle machine is removing water vapor from the air at constant temperature. Remember that latent heat is moved with a temperature that's constant. Sensible heat can be sensed by a thermometer, but latent heat, also known as hidden heat, it's added or removed at constant temperature. So this is no surprise. The addition or removal of latent heat happens during a phase change, and in this particular case, the water vapor in the air is being converted from a vapor into a liquid. If you're wondering what's going on with the oil pressure, remember that I said the seals in this turbocharger really aren't all that great. Now I don't know if this turbocharger really needs to get really hot, like be attached to an engine in order for the seals to seat, or maybe it's just a bad, cheap eBay turbocharger. Who knows? But in any case, it was good enough for these runs. So as you guys saw in those clips, the new demonstrator worked much better than the old one did. So now I'm going to take some time to answer some of the questions that you guys asked me in the previous video. In the last video, I was asked quite a wide variety of questions, but I'm going to cover a few of the basics ones here, such as, the intercooler is cooling the air, why is the pressure not falling? How does the turbine make the air cold exactly? Can I use a small high pressure, low volume compressor to make my own air cycle machine? How about storing compressed gas or air in a cylinder and then releasing it? Can I achieve cooling that way? And I want to make my own. What parts are you using? I'm going to answer a few of those questions for you right now. So to answer the first question, the intercooler is cooling the air, but the pressure is not falling. What's going on with that? And if the intercooler is removing energy from the air, how can it drive the turbine? So we're going to understand a little basic thermodynamics here, all right? There is a relationship between pressure and temperature, that's true, and you might be familiar with the equation PV equals nRT. However, there is no such law that says a gas has to be a certain minimum temperature in order to achieve a certain minimum pressure. The air in the air cycle machine is heated not necessarily because of the pressure that it has, but it's being heated because the compressor is doing work on the air to compress it. The intercooler is not removing pressure from the air, but rather it is removing the heat of the compression that the compressor added to it. So once that heat of compression is removed from that air, it still maintains its added pressure. Now understand that pressure in the air is actually potential energy. So after the air is cooled in the intercooler, it enters the turbine. Now the turbine is going to do the opposite of what the compressor does. Now the compressor did work on the air, but in the turbine, the air is going to do work on the turbine, which makes it spin. And because of that, it's giving up that potential energy, and therefore the temperature is lowered. Do you want to calculate the temperature of the air after the compressor or the turbine? You can do it if you use this derivation of the isentropic ideal gas equation. But remember, you need to use absolute units like Kelvin or Rankine and use absolute pressure units. Otherwise, you're going to get a bad result. That should have answered the first two questions. Now we're going to move on to the next two. Can I use a small high pressure low volume compressor to make my own air cycle machine? Or how about storing compressed air or another gas in a cylinder and then releasing it? Can we do that? So the answer is an obvious yes. This will absolutely work. However, the heat capacity and the density of air is very low in comparison to most other refrigerants. So the cooling capacity is going to be extremely small. Now I've done this before and I've actually reached some pretty low temperatures, but it only had the cooling capacity to cool down just the tip of the thermometer. That's it. You will not be cooling big, large rooms with this. The air cycle machine works because it moves a very large volume of air. So I was actually contacted by somebody who wanted to know what parts I was using in the original air cycle machine. Up on the screen right now is a list of the parts that I'm using in the current air cycle machine demonstrator. I want to reiterate the caution warning that you're seeing on the screen right now. This is dangerous. You should know that. The voltages are really high in this project, and electricity does not forgive your mistakes. If you get hit with this, you could go down and you may not get back up. So you really need to pay attention to what you're doing and proceed at your own peril. I've been working with high voltages for a very long time. I know what I'm doing. It might look dangerous, but I know how to be safe when I'm handling it. So if you're going to try this, make sure you know what you're doing. Just a few more thoughts. So how do they reach extremely low temperatures with an air cycle machine? Well, there's these air cycle freezers, and there's a lot of tricks that these people have up their sleeves to make it work. But primarily, it uses this really neat heat exchanger. It's a regenerative heat exchanger. And basically, air that's flowing out of the turbine goes into one side of the heat exchanger, and the air coming out of the intercooler goes into the opposite side. So in effect, what happens is the air is going in a loop. The air exits the turbine, and that air cools the air that's entering the turbine. And that air keeps looping inside of that heat exchanger, and it gets colder with each pass. And it also circulates inside of a sealed container. It's much like a walk-in freezer. It's really amazing, and I highly recommend that you guys search up an air cycle freezer on YouTube. Amazing how low they can get the temperatures. I really could go on for hours talking about all this, but the final thought is this. How does the efficiency of an air cycle machine compare against a vapor compression cycle, and what are the advantages and disadvantages? So the vapor compression cycle really benefits from the phase change. And like I was saying about earlier, the latent heat. So the latent heat of vaporization in most of these refrigerants is relatively high. And so in the refrigerant evaporator, there's liquid refrigerant that's going to change from a liquid to a vapor. And in doing so, it does this at constant temperature, and it removes quite a bit of energy doing it. So the compressor doesn't need to move a large volume or mass of refrigerant in order to get a fairly large cooling capacity. But this advantage of the vapor compression cycle is also its disadvantage. You see, as the evaporator's temperature falls, the pressure of the refrigerant in it also falls, and that reduces the refrigerant's density. And ultimately what it means is the compressor moves less mass for the same volume. What it all means is that when the evaporator gets cold, the vapor compression cycle loses a lot of its cooling capacity. And this is in contrast to the air cycle machine. The air cycle machine does not benefit from that latent heat of vaporization. It doesn't have a phase change. The air is a gas the whole time it's in a cycle. However, even though it doesn't move as much heat as the vapor compression cycle does, one thing that it has an advantage of is the amount of air flowing through the system is relatively unaffected by the temperature. And because of that, you can reach those extremely low temperatures that we were just talking about. So guys, if it's not obvious, I am very pleased with how well this project turned out. Now, if you're watching this and none of this is making any sense to you, just know this. I have a working air conditioner that uses only air as a refrigerant. While everybody else's air conditioner is leaking out refrigerant, my air conditioner actually leaks it in. Thank you so much for watching and staying with me, and I'm sure I'll have another thing for us to check out at a later date. Thank you so much for watching, and I'll see you on the next one.